Let's get started because we missed a couple Thursday classes, right? Because of some weather, so we're a little bit behind, but we'll probably have enough material that we'll be able to cover the root locus and do the homework. So let's get started. So the last slide, what we talked about was when we do our, oops, it's not working. Where we actually look at S equals infinity or approaches infinity, we saw or we determined that we actually approach the infinite poles or zeros. These are always going to be zeros because we almost always have more poles than zeros. So we have to have the same number of poles and zeros, which means we need additional infinite zeros. But the key thing is we still have to meet this criteria, right? That the magnitude has to equal plus or minus 180 degrees. And the reason why it needs to do that is because this characteristic equation always has to be valid, right? So if we see that over here, we have this negative k times b sub m. So when we pull that out, that's k b sub m, and the angle here is plus or minus 180 degrees. So it actually can vary if it's plus or minus 180 degrees, or it can be multiples of 180 degrees, right? Because 180 is the same thing as 540 and on and on and on. So what we need to do is figure out how do we approach those poles or those zeros at s equals infinity. Because if they're on the real axis, it's pretty easy. It's plus or minus 180 degrees. But in many cases, they will not be. So what we need to calculate is what's called the angles of the asymptotes. And again, the asymptote is just the angle that as you allow s to approach infinity, that's what the root approaches. So it allows you to sort of fine tune your root locus. Minimize this here. So we rework our equation, just stealing this from the previous page. S to the n minus n. Remember, n is the order of the denominator. M is the order of the numerator. We rework it, and then we're just solving for the angle here, okay? We're only going to be focused on the angle because we're trying to solve for something that is an angle, right? That's the angle of the asymptotes. And what we see is we have this r times 180 divided by n minus m. Question? Okay, sorry. So now what we have to do is we have to figure out what those actual specific angles are. So if n minus m equals 0, right, or n is equal to m, there are no asymptotes. Why? See if we think about this. Why are there no asymptotes? Because the number of finite poles equals the number of finite zeros, right? So how many poles that are, how many zeros at s equals infinity do you have? 0. Because if we have s squared over here and s squared over here, right? We have 2 poles and 2 zeros. We don't have any infinite zeros. So there are no asymptotes. Kind of makes sense. If we have a difference of 1, then we're going to approach it at plus or minus 180 degrees. 2, plus or minus 90. 3, plus or minus 60, and plus or minus 180 degrees. 4, plus or minus 45, or 135. And that's basically all we have to worry about. We probably will, I mean, you could continue on, but we don't have to worry about it. And then I'm not going to define this or show how the derivation for this necessarily, but where do the angles of the asymptote intersect? Because remember, you have to have 2 asymptotes, because if you leave the real axis, you have to have complex conjugate pairs. So you have to have 2 asymptotes if you're approaching it at plus or minus 90 degrees, right? If you do it at 180, you don't have to have complex conjugates because you can stay on the real axis. But plus or minus 90, you've got complex conjugates. So that means you have 2 asymptotes. That's why it's plus and minus 90. And they have to figure out where do the asymptotes exist. What's the start off location? And that's what the sigma sub a is. So you sum the finite poles, you subtract the sum of the finite zeros, and then you divide by n minus m. So here's our third rule, right? Remember our previous rules? First rule was we have to start at a pole and end at a 0. We have to start at a pole, end at a 0. Second rule is we have to have complex conjugate pairs if we do have complex numbers. Third rule is if you have any zeros at infinity, you're going to solve for the angle of the asymptotes using this equation, and you're going to solve for where they depart the angle of the asymptote. Sometimes we call that the centroid. All right, so let's take a look at an example. We have a system with a variable value of k here, a variable gain quantity. And what we're going to do is we're going to allow that value of k to go between 0 all the way up to infinity. Clearly, we want it to be 0 because we would never have any output, right? But just for mathematical purposes, we'll allow it to start at 0. And now what we need to do is we need to draw the root locus for all the points. So first thing we do is we see that the order of the numerator is 1. The order of the denominator is 4. So I'll put s to the 1. So this is equal to m, and this is equal to m. So n minus m is equal to 4, right? No, 3, 4. It's 4 minus 1. So now we can start writing in our poles and our zeros. So our poles, 0, minus 1, minus 2, minus 4. Our zeros, minus 3, and 3 at s equals, or s approaches, infinity. Where did I get the 3 from? Right here, the n minus m. Okay? So now what I need to do is I can actually start drawing my root locus. So let's do that in whiteboard. Sorry about that. I thought I had cleared this. All right, so first thing I'm going to do is start marking the direction of my poles. 0, minus 1, minus 2, and minus 4. And I'm going to go ahead and start to identify the zeros, but only the finite 0. And the reason why I only do the finite 0 is because I don't know, as s approaches infinity, does it approach it from the real axis? Does it approach it from, complex conjugate pairs? I don't know. But what I do know is that I start at a pole and I end at a 0. So I know that I have a root locus that goes over here, right? They're starting at a pole and ending at a 0. I haven't ended. You can see I started at a pole and I'm ending at another pole, at least if I stay on the real axis, but I can't end at a pole. So I know I have to leave the real axis at some location. And what we'll learn in a little bit is there's not going to be any root locus over here. So now I'm going to start at a pole and end at a 0. Perfect. I can end there. You can see how I can end at that 0. So this one ends. That root locus ends. I don't have anything over here because I'm not starting, and I can't share the same 0, right? I can't start at a pole and end at a 0 that's being ended by another 0. So what happens over here? I'm leaving over here. Where do I go? Go to infinity. So this is going to go out in that direction. So that tells me immediately I have one pole at s approaches infinity, or 1, 0, I should say. And so it's going to go way out over here. Now the question I have is, check this root locus is complete. Check this one is complete. Can I check these two off? No, because I haven't ended at a pole. And since I have to leave the real axis, I have to figure out where I leave and where I terminate. So I'm going to have a couple of poles that go up to, or a couple of zeros that go up to an s equals infinity. So someplace on this graph, I'm going to have to go ahead and show that. So now I'm going to have to go ahead and calculate the angles of the asymptotes. All right, so I have r times 180 divided by 3, because n minus m is equal to 3. That's where this comes from. And when I divide that, I got plus or minus 60. plus or minus 180, et cetera, et cetera, et cetera. I've already got this plus or minus 180. I checked it off, right? Because I saw that as I approach here, this is, we could also draw, let me put, change the color here. Let's put a silly color. This is an asymptote right here, right? That angle is 180 degrees or minus 180 degrees, right? I can go in either direction. I still get to the same location. So that validates one of my asymptotes. The other asymptote I have is 60 degrees, right? Right here. So now what I need to do is I need to calculate the sigma sub A. Why didn't I calculate the sigma sub A for the 180 degrees one? Doesn't matter, does it? Because it's 180 degrees. So I can start it at this location or this location. It's going to go to the left, right? All the way out. So it doesn't, you don't calculate it for 180 degrees. It's not relevant. I do need to calculate it at 60 degrees. So I'm going to sum the finite poles and subtract from the finite zeros. And here's, we're going to be careful. I'm summing these numbers here. Okay. I'm not summing the positive 3. I'm summing the actual poles. So I have to sum 0, minus 1, minus 2, and minus 4. And I have to subtract from that the zeros, the sum of the zeros, and there's only one, that's easy, minus 3, and divide that by 3. So you end up with negative 7 minus 3, which is positive 3, which is 4. So I have minus 4/3. So I have to leave somewhere around minus 4/3, and it approaches it at plus or minus 60 degrees. Now that's the angle of the asymptotes, right? That's where they originate at that particular location. But that's not the same thing as where this point leaves here. Okay. So I have the angle of the asymptotes and the center point for the asymptotes, but it doesn't actually tell me where I'm leaving the real axis. That's going to be called sigma sub c, the centroid, and we'll show how to calculate that in a second. But any questions on how to calculate or solve for this? Just basically laying it out. And what I've done is I've got all the real axis points for my root locus. I don't have anything outside the real axis, but I have all the real axis. And I also know where I'm going to terminate when I get to S approaches infinity.
Where 0 and -1 leaves.
Yes. Yep. And they have to come together to the same point because you have to have complex conjugate pairs. So that tells you where you leave. We'll see that in a moment, but I want to make sure everybody sees where we get the asymptotes. Good for that? Okay. And then over here on the right is just some discussion about, now let's go ahead and solve for the open loop transfer function, and then do the closed loop transfer function and actually put all the K terms like that. We're setting up for where the centroid, we're going to calculate the centroid. This is where you can see the MATLAB. So you're going to allow MATLAB. You can do the root locus plot. And remember, it's just a function. You set up the transfer function and you do RL of the transfer function. So we have the asymptotes. And we have those terms there. Now watch K as it increases. Hard to see, but if you look at the lines, they're getting further and further away. Now they leave the centroid, the ones on the right, but look at the ones on the left. They're just going from their poles to their zeros. Now you can see that I'm approaching the asymptote at plus or minus 60 degrees. Now, one other thing, remember how I said over here that this stays on the real axis? Is there another indication as to why that stays on the real axis? When can I leave the real axis? What has to be the rule? What was rule number 2? You have to have complex conjugate pairs, right? To be able to leave the real axis. How many roots do I have over here? I only have one because I started a pole. Where's my other pole that I started from? It's nowhere on here. So I can't start at a pole and have another root locus go there unless I can start at a pole. So the only way that I could have two root loci living on the real axis, maybe going towards each other or going away from each other, is if I have two roots. Exactly what I have right here. I have two roots, two poles, I should say, at that location, which means I have two root loci that live there. That's allowed.
On the end, right, you find plus minus 60 and then plus minus 180.
Yep.
Then consider the 180 for the plus minus 4.
It's actually more for the root that starts at -4 and heads to infinity. Remember, that's a root locus that continues on.
Yeah, but not about the 1 minus 3.
Ah, excellent question. What happens at -3? Remember the rule about starting at a pole and ending at a 0? I start at a pole, -2, and I end at a 0, -3. Why would I go out to s equals infinity if the root locus is done? It ended. This is as you increase k to infinity, it's only going to ever get to -3. So it doesn't continue from there. It stops right there.
But then why you get the 1 minus 4 or 1 minus 3?
Because where's my 0 to end? I need to end the root locus, right? Start at a pole, end at a 0. I need to have a 0 to end at. I do have one to end at s equals infinity. That's why it approaches the 0 at s equals infinity, and that's why I can calculate an asymptote. No asymptote here because I'm not going to a 0 at infinity. Question?
Yeah, why? Did it, that's, did it go to the left side, is that just, that's one?
Nope. Because I can't go over here. There's no root locus that goes there. So to me to start going to the right,
Well, there was the S, then it was on the right, that the -4 will go to 3. And then the 0 will go to infinity, and -2 and 1.
yeah, but I can't live here first off. And then if I went over here, now I have two root loci on the real axis. I can't have the two unless I have two poles that originate on the real axis. So this is no root locus in this location. There's no root locus there. So the only way I can get over here is I'd have to jump away, right? And jump in, back in, which I can't do unless I have a complex conjugate. Don't have a complex conjugate, so I have to stay on the real axis. So I can't go to the right, I got to go to the left. And hopefully, when we drew this out, we actually saw that that was the case. Okay. Making sense, sort of, kind of?
But then that's like the various configuration of you have, right? This is the you could say that the pole at -1 should have went to the other 0 and leave on the outside.
So the ones at -1 and 0?
You want the one at -1.
Okay, fine, but remember the rule, I have to have a complex conjugate. So what Barzilay said is, and I'll just pick green. This one would go this, oop, I changed to green. This one's gonna go this way, correct? The problem is, if that goes this way, this one still has to start. I have to end at a 0. Where's my 0 to end at? It's not on the real axis, so now I have to jump off the real axis to end at a 0. But the problem is, I don't have a complex conjugate over there. Because that pole that is at s equals 0, you're telling me the root locus goes to the right. So I can't get my complex conjugate pair to work here. So it's got to go to the left. Okay. This is why those two rules are really important, right? We start at a pole, end at a zero, rule number one. Rule number two, if we leave the real axis, we've got to have complex conjugates, which really locks us in. That's what the math tells us. We can't get there from here unless we have a complex conjugate. So that's forcing us to go in direction. All right, so we talked about animating it. You can actually draw, this is just if we did it by drawing it, you can actually just, you can show the root locus by doing a polar plot in MATLAB, and you can show the angle of the asymptotes. So you can see this is the actual plot, and this is what we have by showing the asymptotes. All right. Okay, so now let's talk about the root locus on the real axis. So all valid points have to satisfy, right? If it's an actual root, the 1 plus kgh, the characteristic equation, has to equal 0. We've already said the angle of kgh has to equal plus or minus 180, plus or minus 3 times 180, etc., etc. So we can simplify that, and we can say that the sum of the angles of the zero has to be minus the sum of the angle of the poles has to equal plus or minus 180 degrees. Do you remember when we first introduced that? When I said, oh, there's a bunch of numbers here. And I showed you how to do the calculations when we plugged in a root at S equals A plus JB. And these became magnitudes and angles, right? And then we just showed you how to add and subtract, multiply, and divide. Can you see why I did that now? Because these are angles of the zeros up here, right? These are angles of the poles, right? So when I did the complex math, remember when we do complex polar numbers, how do you add and multiply and divide? You multiply the magnitudes and you add the angles. And if you divide the magnitudes and subtract the angles. When I multiply these two, I add the angles, right? When I divide by complex number and polar, I subtract those angles, correct? So can I just rewrite that mathematically as a sum of the theta, the zeros associated, the angles associated with the zeros, minus the sum of the angles of the poles at that specific number? And we know that that has to equal 180 degrees, plus or minus, or the multiples, right? So we said that the phase of the zeros. So now let's take a look at some test points. Let's do a test point. So do you believe, or do you think that we have all the way out over here? Do you think that that's actually going to be a root locus point? We're just picking a test point. Maybe. What do we have to know? We know that the angle here has to be plus or minus 180 for it to be a valid test point that actually lives on the root locus. So let's check it. Well, we'll do our phase calculation. We'll look at our phase angle. 0 minus 0 plus 0. Does that equal plus or minus 180 degrees? Does not, right? 0 degrees. So it's not plus or minus 180, it's 0. So that's not a valid test point. How about over here? Let's check out our phase. So our phase, we have 1, 0 at an angle of 0, minus 0 plus 180 degrees. Is that a point that is on the root locus?
What of the 0 and 1 example?
So let's just say that this is S plus 1 over S minus 1 times S plus 2. That's the open loop transfer function. So what we're doing is for a test point right over here, our test point is going to be between minus positive 1 and minus 1. So we're basically saying, let's just say S equals positive 0.5. We're just trying to figure out what the angles would be by plugging in positive 0.5 to here. And will we get what will the angle be in that? Everybody understand what I'm saying there? Okay, so let's plug it in. So remember, our angle has to be this. So if I plug in, whoops, what happened? If I plug in 0.5 for S, let's see, will I get? Hold on, let me do this. Oh. All right, so let's say that we have S. This is not the origin, so we'll say that this is S plus 1. I'm sorry, S plus 2 over S plus 1 times S plus 3. Okay.
What do you get the F?
Well, I'm just picking points so that let's just say this is minus 2. This is minus 2. This is minus 1. And this is minus 3. Okay, those are the original ones. So now I want to check and see. Let's go back and put a test point over here. Let's say that that's 0.5. Okay, so now I'm going to check and see S plus 2 over S plus 1 times S plus 3. And I'm going to evaluate that at S equals 0.5. Again. And see if that's a valid point. So I have 2.5 over 1.5 times 3.5. What are the angles associated with 2.5? The angle with 2.5 is 0, right? What's the angle associated with 1.5? 0. What about 3.5? 0, right? So what we have is we have the angles 0 minus 0 plus 0. That's what we have there. Okay, I just picked 0.5. Now I'm going to pick a test point that we know is between minus 1 and minus 2. So let's pick, let me copy this over here because I'm running out of room. So looking at this plot, I'm going to pick a point over here that I know is between minus 1 and minus 2. So let's say that S is equal to minus 1.5. Do you agree that minus 1.5 is between one? Thank you. You had to say it. Do you agree that S equals minus 1.5 is between minus 1 and minus 2? Seems like it, right? That's pretty easy. All right, so minus 1.5 plus 2 all over minus 1.5 plus 1, sorry, I'm jumping ahead. All right, now I'm going to calculate that. We have 0.5 over negative 0.5 times 1.5. Whoop. Everybody agree with that? Now we're going to treat these as complex numbers, even though they're real numbers. So this is 0.5 at an angle of 0, divided by 0.5 at an angle of minus 180 or plus 180, doesn't matter. I will put plus, and then times 1.5 at an angle of 0. Now we're going to check the angles to see if it's plus or minus 180. 0 minus 180 plus 0. Does that equal plus or minus 180? Yeah. So that's a valid point. So all we're doing is we're looking for points to see if we're gonna get angles of plus or minus 180. If I put a point over here to the right of that pole, no deal. I put one over here to the left of the pole, we're good to go. Your turn. Try minus 2.5. I give you 3 minutes. Remember, you're using this. Oop, why isn't it working anymore? That's your open loop transfer function you're going to use. That's, you got to check, use that open loop transfer function. This one right here. Zero? Let's try it. So now we're going to do the same thing. Ooh, doesn't work. Okay.
Zero.
I don't know why it's not working anymore. Minus 2.5, right? That's a valid point. So what we have is minus 0.5 over minus 1.5 times 0.5. So that's going to be equal to 0.5 at an angle of 180 divided by 1.5 at an angle of 180 times 0.5 at an angle of 0. So now we'll do our angles. 180 minus 180 plus 0 equals 0. So is that a valid point? Minus 2.5? It is not, because it's got to be plus or minus 180. So that tells me that I have a root locus that lives here, but none that live here, because I just tried a random test point. So here's that 2.5. We get 180 minus 180 is equal to 0. How about over here? You want to do 3.5 real quick? Let's try 3.5. So I'll just do it really quickly. So it's minus 3.5. So I got, it's working. Why is it working? So minus 3.5 is going to give me minus 1.5 in the numerator, minus 2.5, and minus 0.5 here. That's going to equal 1.5 at an angle of 180 over 2.5 at an angle of 180 times 0.5 at an angle of 180. When I do my angle calculations, 180 minus 180 plus 180 equals minus 180. Is that a valid point? Sure is. So I have root locus points over there. Okay, so that's the fourth rule. big one right here. Where do you find it on the real axis? It's always to the left of an odd number of open loop poles and zeros. Okay? And the reason why it has to be odd numbers is because you need it to be that plus or minus 180 degrees. If you did it for even numbers, they'd always add out to 0. So how do I know the odd poles and zeros? I start labeling them. This is pole 0 number 1. This is pole 0 number 2. This is pole 0 number 3. Notice I'm not saying it's pole 1, 0, 1, pole 2. I said pole /0, 1, pole /0, 2, pole /0, 3 that live on the real axis. So it lives between odd and even, right? It only lives on the real axis to the left of an odd pole or 0. So it lives here. Once I get to 2, am I to the left of an odd pole or 0? No, because 2 is an even number, so I stop. Same thing over here, only lives to the left of an odd pole or 0. So another way, we go back over here. Do you remember how I said it lives between here, here, and here? Because internally in my head, I labeled this as, see if I can change it to another color. This was number 1, pole 0 number 1, pole 0 number 2, pole 0 number 3, pole 0 number 4, and pole 0 number 5 that live on the real axis. This is not all poles and zeros. This is just the ones that live in the real axis. So it lives between these two, because that's to the left of an odd number, but not between 2 and 3. It does live between 3 and 4, to the left of an odd number, but not between 4 and 5. And to the left of an odd number, between 5, and then again, eventually it has to terminate at infinity. So that's how you know where they can draw those on the real axis. Okay, questions on that? Good so far? All right, so let's go back to our example and let's see if it validated. Here's our root locus, and we can append. This is 1, 2, 3, 4, 5. And I can see that it lives between 1 and 2, but not between 2 and 3. It lives between 3 and 4, but not between 4 and 5. And it lives from to the left of 5. All right, so now the last thing we need to do to really be able to draw the root locus is, if you remember going over here, where did we leave? That's the breakaway points, the centroid of the breakaway points. So how do we calculate that? Well, we talked about living between the odd numbers and poles and zeros. So we know in this particular example, we have to live over here. So great, I start at a pole. And I start at a pole, and we know it has to live between the odd and the even, but not the even and the odd. And I have to end at a 0. I'm not ending at a 0. I've got a couple zeros over here that they need to end their root loci. So I haven't met, right? I haven't terminated my 2 root loci that started between those 2 poles. And I haven't started the 2 poles, or the 2 root loci that need to end between those 2 zeros. So that means I have to leave the real axis, which is okay because I've got 1, 2 root loci over here, and I have 1, 2 root loci that live between there. So I'm going to leave my real axis because I have complex conjugate pairs. All right, so I've used all those rules. I've got my, I can calculate my asymptotes, but do I really need to calculate these? No, why not? Yeah, very good. There's no poles at s equals infinity, right? So there are no zeros at s equals infinity. So I don't have any angles to calculate because I don't have them. They don't exist. So where do they depart? Where do they arrive? All right, so let's just look at a picture of when k equals 0. When k equals 0.7 is when they leave. Now we're going to increase k until they get back to being purely real. And then we're going to continue to increase k until it reaches infinity. So that's our starting at a pole and ending at a 0. But the question is, how do we get there from here? So let's do some plotting. So now we're looking at our plots, and this is the magnitude of the plot. You can see k. And look what happens at k when it's between those 2 points. Are you noticing anything important? Let's go back up again. Look what happens when you leave the real axis. Look what happens with the gain of k. Keep watching, keep watching. Gone. I left it. Look when I arrive. Did you see?
Yeah.
Well, so when you see the poles, they're coming really close to a same point, right? Then they stop. Look at the same thing for the zeros. See right here? They're at that point. What do you notice about those? Anything specific? They're maximum and minimum points, aren't they? So is there a calculus tool or technique that you've been able to use in the past to calculate maximum and minimum?
Yep.
What is it? Max and min points in calculus. What is the slope of the line of a maximum or minimum point? 0. So all you need to do is take the derivative of that characteristic equation, set it equal to 0, and you've got your points. So just a summary here, right? Our points occur where we break our way when k is equal to k max, and then our break-in point occurs when k is equal to our minimum k, at least in terms of those plots. So if it's complex, if k is between 0.07 and 14. So take the derivative. And what we're going to do is we're going to take the partial derivative of k with respect to s, right? Because we're looking at plots. And we're going to set that equal to 0. That's when the slope of the line goes to 0. So we're just going to go ahead and take the partial derivative of the -1 over g times h. So here's our open loop transfer function. Take -1, take the derivative of it. And this is where it gets to be a little onerous, because taking a derivative of this, right? You got to do the quotient rule to go ahead and do it. So it takes a little bit of time. But the derivative of this is this mess right here. Okay. And when I combine those into one equation, I end up with this. Now I got to solve for the roots of that, right? Set that equal to 0. So really all the roots that I need to solve for is here. What's that? Yeah, you don't even need the 2, because the 2, you divide both sides by 2 and then it factors out. So only really need the roots of 2 lambda squared plus 10 lambda plus 11. That's what we have here. Solve for the roots, and we get this. Interesting. We have 2 roots, right? Which is right. Is it -3.4 or -1.63? Or can you not tell? Sounds right? Are they both right? Think about what in the example, in this example, it's not too bad. But we have to have 2 points. We need a break-in point and a breakaway point, right? Yeah, exactly. So we know that our root locus, oops, we have 3 and 4 and 1 and 2. So we break away at -1.634 and we break in at -3.366. Why? Because those 2 points live there, right? They have to be valid points So you have to actually have those that live on the root locus. Okay? Questions on that? Say that again?
When we did
When I did the derivative of this,
yeah, so those 2 points, they are on the axis.
well, not necessarily. In this case, they were both on the real axis, but they don't, and where there's a root locus that lives. But they don't always have to be on the real axis where there's a root locus. Sometimes you'll get them.
And then even right now, going to show the first way, but then when you split it in the picture, you didn't split that.
I didn't what?
When you split it in the previous slide, you didn't. Yeah,
Yeah, one point's right here. And the other point's right here. So I didn't highlight it, but that's the actual calculation that you get that.
just, well, it looks.
The two pictures below?
Yeah.
Yeah, because this right here is a plot of the gain. This is not the root locus, that's the gain plot. Remember, what I'm trying to do is I'm trying to find the maximum and minimum of the gain so that I can actually use that to calculate where it leaves the real axis. I don't actually need the value of K. I just need to know when that slope equals 0, then I have a valid root locus.
But when did the K get, how did you do from the 4 here to when you get to, onto, between, and 4 and 3? Well, I'm going to see the line go that side and, from the 4 to 0.
So I'm leaving here and this and here and this. So I have complex conjugate pairs to work with, right? That's why I'm breaking away from the real axis and then I'm breaking into the real axis. I calculate 2 points.
Yes.
Guesstimate what lines? The plot of those?
Yeah.
Those get to be a little bit harder. But you can calculate all these points because remember, go ahead. Well, you have to make sure that the magnitude and the magnitude of the gains, so whatever value you calculate. So here's my characteristic equation. That characteristic equation evaluated at S equals a valid root has to be equal to K, or sorry, 1 at an angle of plus or minus 180 degrees. Actually, it's not it's is it the characteristic? Yeah, I can the characteristic equation. So it has to be equal, not the characteristic, it's a open loop transfer function. Evaluated at that value has to be equal to 1 plus or minus 180. So you have to go ahead and pick a point and then see if it reaches out there. There is some refinement, but when they get this kind of shape like this, they're a little bit harder to draw. The easier one is the one when we have not the same number of poles and zeros, we have to leave the real axis. The one where we have those asymptotes going out, those are a little bit easier to calculate. So just summarizing here and here. So that's where our breakaway point is. Evaluate there. All right, so since we're good, help me out here. Find, is it the breakaway point or the break-in point? The waypoint, the BA point. Why am I doing the BA point? Because I break away right there. So can you help me find the breakaway point? All you have to do, take this equation, set it equal to 0, and you have the value of K. You know what the equation for K is. Know how to do that? You do. I'll copy this over to here. And then I also need the transfer function, right? So I gotta go up a few slides. I can't remember that was off the top of my head. Well, we had one here, right here. H is 1, yep. Okay. So you have to find K first. So K is going to be equal to -1 over S plus 3. And this is where I recommend, this is just a recommendation, but multiply everything out to make it work. So I have S squared plus S times S squared plus 6S plus 8. And that's going to be equal to S to the 4th plus 6S squared plus 7S cubed, right? I've got that correct. Hopefully I've done that correctly. And then let's see, I need, let's see, plus 14S squared plus 8S. Is that correct? Did I have that done correctly? I think I have that done correctly. Anybody have any issues with that? So this becomes S to the 4th plus 7S cubed plus 14S squared plus 8S. Now I'm going to invert it. Right? Now I'm going to take the derivative of that. Let's see how good we are doing derivatives. So the partial, actually it's the derivative of K because it's only a function of S. Going to be equal to, what's the quotient rule? Do you remember? Derivative of the numerator times the denominator minus the derivative of the denominator minus the times the numerator over the denominator squared. So that's going to be 3S, 4S, yes. 4S cubed plus 21S squared plus 28S plus 8. All of that times S plus 3. What's that? The derivative of.
Oh, okay, you look that, okay, good. Yeah.
Let's say, did I forget how to do calculus?
Oh, yeah. Okay,
All right, so then now we subtract from it the derivative of the numerator, which is just 1, right? So that's an easy one. So times S to the 4th plus 7S cubed plus 14S squared plus 8S. And now I have to square this, but I really don't need this. Why don't I need this? Because I'm setting that equal to 0. So I really can get rid of the negative here. And I can also get rid of that there, right? So now you have 4S squared plus 21S squared plus 28S plus 8 times S plus 3. So let's see if I can do this one. I've got 4S to the 4th. Plus, let's see, I have 21S squared, S cubed plus 33S cubed. 28S plus 24 is 52S. And then plus 24, if I did that correctly, not guaranteeing it, but that's what my hope is. Oops, this is S. I think I did this. This is incorrect here. Let's see. 4S to the 4th, that one's fine. And then I have 21s squared times s, which is 21s cubed. Yeah, that's correct. And now I have to get the s squared one, so I have 28s squared plus 21, so that's 49 s squared. And then I have 8s plus 28 is 36s plus 24. No, that's not correct. Sorry. It's 3 times 28. This is, like I said, this is where it gets harder. So 3 times 28 is 84s plus 8s, 92s plus 24.
But 28 squared plus.
Oh, you're right. Geez, I keep making mistakes. See, this is where it's easy to make mistakes. So 28s squared plus, no, 28s squared plus 21s squared, right? That should be 49s squared. Yeah, it's 21s squared. Oh, you're right. 63. So 63 plus 28 is 91. All right, so we got the 91s squared. So now we got to get the s term. So we have 8s plus 84s is 92s. So this is where it gets hard, right? And set that equal to 0. Does that look right now? Because if it's correct, and we'll find out soon enough, we'll take the roots of 4, 33, 91, 92, 24. So minus 3.33, minus 3, minus 1.53, and minus 0.39. Which one of those is right? We have 4 of them. It has to be the one that lives between 1 and 2. Which one lives between 1 and 2? The only one that's valid is minus 1.5309. All the other ones are invalid, right? Because where I'm breaking away has to be between 1 and 2. It's not going to be minus 0.39 because that's not valid. It's not going to be 3 or minus 3 or minus 3.0 because those are over here. So the only valid one I have is minus 1.5309. So I can append to here. And this point where I leave is minus 1.53. What did we say? 5309. And that's how you can calculate that. That one can be a tougher one, but it's doable. Okay.
But then you, the other side, find the one with J9.
I can do that here, but I don't need it. All I'm trying to do is draw the root locus. If I actually had to say a case where I said, figure out the points where the maximum value of K or what K needs to be so that you can get, you can only get real poles, then you would do this part. And you can see that over here.
Yeah, you find that.
Right, so I have the values of K over here. And so once I have that, now all I need to do is plug these values into this equation, actually solve for those values of K. Right? So when I do that, and this still, remember, this has to be equal to, so these are valid points. You don't actually have to check to see if it's 1 at an angle of 180. So if as long as those points are correct, then all I have to do is just evaluate this equation and solve for K. All right? So that's that last step. So we see that over here. Here's our K max. We have those points. Here's our root locus stuff. Last little bit. Angles of departure and angles of arrival. what are the angles of departure and angles of arrival? Well, what if we actually terminate or start, either one, we can start or terminate at complex conjugate pairs. So you can see over here, if I do the quadratic equation, negative b plus or minus b squared minus 4ac all over 2a gives me, oops, negative 1 plus or minus j1, right? So you can see that those numbers are complex. And my root locus now is a lot more complicated because I'm not starting on the real axis. I'm starting in a complex number. So now what I need to do is figure out, where do I go? Where do I go from here? Well, using some intelligence, remember one of our rules is the root locus always exists to the left of a real pole or zero. So if I label this 1 and 2, then I start at my pole and I end at my 0. So I have one pole at -3 and 1, 0, -2. So that root locus terminates. Over here, I have no poles. I have 2 poles, but I have no zeros. So I'm not going to terminate and go back to the real axis because I don't have any real axis poles. Or I should say real axis zeros. Even I'm getting confused. So this one is going to actually start to peel away and then go off to s equals infinity. So what are the angles that this takes off at? What is that angle right there? So we're going to consider a point near, quote unquote, one of the complex poles, as close as we can be. And remember how we said that all those angles individually have to equal 180 degrees? Plus or minus 180 degrees? We still need to make sure that that's the case. So what we're going to do is we're going to calculate our angles and see what we get. So if we're really close, we can see that the angle for our pole number 1 is 90 degrees. Or the angle here. Oh, this one is a little bit harder. You have to calculate it. Theta Z1 and then theta P1. And then the rest of those has to make up that 180 degrees. So that's that departure angle for theta P2. We're going to calculate it by our characteristic equation. Again, has to be 180. So our departure angle, which is theta D, has to be placed into that equation. So theta Z1, because it's 1, 0, minus theta P1 plus theta D plus theta P3 has to equal to R times 180 degrees. How do I calculate those angles? 45 degrees for theta Z1, minus 90 degrees theta for that P1. Theta D is unknown. And then my last one is the inverse tangent of 1/2. How did I find what? So remember what we said? We have to have our angles. What is the real part and the imaginary part to get back to that point? Does that make sense? I'm trying to calculate this angle here. So how do I calculate that angle? This is a triangle, right? What's that? Okay, so what does Sakatoa say?
Oh, yeah.
You got to use arctan, which that's what we did right here. The arctan, we've got to go from this point, right? We have to go calculate that angle. We have to go -1 and up 2. For theta P3, same approach. To do theta P3, you have to go ahead and calculate. So I have to go up here. So how do I calculate that? I've got a right triangle all the way here, right? How far did I have to go in this direction? 2. How high up did I have to go in this direction? Can you calculate the angle there? This one is 90, right? Because basically I had to go 0 in the X direction, lined up with it, and I had to go straight up. That's 90 degrees. This one I had to go 2 and up 1 to rotate that angle. That's where I get this one. How come you didn't ask me about the 45? Isn't it the same approach? Where, let me change the pen color. I have to go 1 in this direction and 1 in this direction. What is the inverse tangent of 1 over 1? 45. And remember, Sakatoa says the tangent of theta is going to be equal to the opposite over the adjacent. So the opposite for this one is 1. The adjacent is 2. So we have to go up inverse tan of 1 over 2. All right, so when we add that up, this angle of departure has to be minus 252 degrees. Okay, that means we have to rotate minus 252 to get that first point where it leaves. How about you guys calculate what the angle of departure needs to be over here? Can you do that? Go ahead. I'll help you redraw it. I'll take a picture of the whole thing. All right, so now I'm looking for this angle of departure here from that point. So all you need to do now, let's change some colors. Let's do this crazy color. So I need to calculate this angle here, right? I need to calculate, hopefully you can see it, the angle that goes down over here. And then the angle that goes down over here. So hopefully you see this one without even thinking about it. This is minus 90 degrees, right?
Minus 45.
Well, let's do them. So we have our theta Z1. We have to calculate our theta Z1. This is the only theta. So let's go theta Z1 minus, and let's go ahead and do these all together. We have theta, we'll call this P1. So we'll call this theta P1 plus the angle of departure plus theta P3. Those are the 3 angles that we have. So our theta Z1, we can find that by taking the inverse tangent. We have to go over to the right 1 and down 1. So that is 1 over minus 1, right? Wait a minute, is the opposite over the adjacent. So it's actually minus 1 over 1 because we go to the right 1 and down 1. Then we're going to subtract from that our theta P1, which we've already said, and hopefully you see it is 90 degrees. Then it's our theta of departure, and then our theta P3 is the inverse tangent of, we have to go to the right 2 and down minus 1. Minus what?
90.
Yeah, that's what I said, it's 90 right here. Oh, minus 90, yes, thank you.
Goes out the.
Yep. So we have minus 45 plus 90 minus theta d. And then what was the inverse tangent of 1/2, 1/2?
Oh. When you have the 90, you get 31.5.
So negative tan of 1/2 is, can't be right, because
So
inverse tan of 0.5 is gonna be less than 45 degrees, right? What is it?
26.5.
Negative, right?
Yeah, minus.
26.56. And that has to equal plus or minus 180 degrees. So we just solve for theta d. And we'll do 180 plus 45 minus 90 minus 26.56. And then the other one is minus 180 plus 45 minus 90 minus 26.56, because it goes in both directions. So it's just the plus and the minus. And so when you calculate those out, you end up with the angle over there. Okay. It should end up being the same angle.
Yeah. Oh, the same angle?
Well, positive 108, if I go positive 108 in this direction, that's the same thing as minus 252. So it looks like it's around 150 something, positive 150 something, or minus 130 something, give or take. But that's how you, if you have to do complex numbers. So here's sort of the formal one, which the angle of departure for complex poles arrives at complex 0. So you have the theta d is equal to sum of the theta z's minus the theta p's plus r 180 times 180 degrees. That's just formalizing it. Or your arrival angle, so you're approaching the 0. So the first one, the departure, is you're leaving a pole. The other one is you arrive at a 0. So you do the same approach, and you just take the sum of the theta p's minus theta i's. And you have to do that for each complex conjugate pair. So you basically do it at the number. And how do you calculate these? You just use those angles. All right. Last little bit. Now, I won't actually present this because I think I only have a minute left. Think about this. In our example, right, that we've been doing here. We cross the j omega axis, don't we? Because the angle of the asymptote is plus minus 60 degrees. So we're crossing the j omega axis. So the question is, where does it cross the j omega axis? Have you been exposed to a tool at this point in the semester, or up to this point in the semester, that you might be able to use to solve for those j omega axis crossings? Anything?
Angle.
It's not even a root locus thing.
Really?
Really? Do you remember anything?
Is it the
How
Ruth
about TV
Hurwitz?
land? Drew, are you trying to talk? Because your screen says you're trying to talk, but I can't tell.
Yeah, can you hear me?
What's that?
Can you hear me?
Yes, go ahead.
All right, was it Ruth Hurwitz?
Ruth Hurwitz. Remember when we had a row of zeros? You found the auxiliary equation. And what did you do when you took the auxiliary equation? set that equal to 0, and what does it tell you? The complex roots, purely complex, and that's where you actually have J omega crossings. So use the Ruth Hurwitz.
I mean, you could just.
You can, but remember, you don't always have MATLAB to do that. And this is a design thing too, right? So you're trying to figure out how to do some of the design stuff. So you would do Ruth.
So
Ruth
there's
Hurwitz.
one question on this test, basically.
Well, I might break it up into separate parts, like what are the angle of departure? Draw this. Tell me the J omega crossings, that type of stuff. But we also have steady state errors for the next test, and our next test is next week, right? Next Wednesday?
Yeah.
We don't have a choice. We have to do it either this week or next week. You'd rather have your final count for like 50% of your grade
No.
or 35% or something like that? 20 plus 15? That's a lot, so. So what we'll do is we'll finish root locus up on Thursday, and we could do some practice examples or whatever. And then on Tuesday, we'll do an exam review, and then we'll have the exam next Thursday. Or next Wednesday, which is gonna be hard because my other class also have to have an exam next week, and so everybody's complaining, saying they want the exam next Thursday. They don't want to do it during lab.
What? Who's that? Who's that?
Different class. You don't have to worry about that unless you want to. All right, I think we're out of time, right? So. Oh, wait, a question.
Oh, this, I guess just more for flexibility for people, for the lab that started making it. We have to be the secret project for them.
We won't have lab the final week of classes.
Oh, okay, never mind.
So next week will be, you have a lab this week, next week you have an exam, and then you'll have no more lab coming up. Yeah. Any questions? All right, if there's no other questions, have a great day. And I will see some of you in a little bit. If not, I'll see the rest of you on Thursday. Take care, everyone.
Thank you, Bob.
Thank you.